Good afternoon, everyone. Welcome to our seminar, Stat Math Unit seminar. Our today's speaker is Hemant Mishra from ISI, and he would be talking on differential and subdifferential properties of symplectic eigenvalues. Welcome, Hemant. You can start.
Yeah, thank you, ma'am. Hello, everyone, and I hope everyone here is safe and well during these uncertain and unprecedented times. And I really appreciate you all joining in. Today's talk is based on my PhD work at Indian Statistical Institute, Delhi, under the supervision of Professor Tanvi Chan. I'll be talking about some differential and subdifferential properties of symplectic eigenvalues. I'll begin with giving you some background on symplectic eigenvalues, and then we will move on from there. I'll get started with some basic definitions. By J, we'll denote by J the 2n cross 2n matrix in the block form 0 identity minus identity 0. Here In is the n cross n identity matrix. A 2n cross 2n real matrix M is said to be a symplectic matrix if it satisfies the condition M transpose Jm equal to J. So if the columns of this matrix M is given by the vectors U's and B's, then the condition M transpose Jm equal to J is actually equivalent to these set of equalities for all ij with respect to the inner product on the Euclidean space R2n. So inner product of Ui with JVJ is equal to chronicle delta Ij, and inner product of Ui with JVJ is equal to inner product of Vi with JVJ equal to 0 for all Ij. And conversely, if you take any 2n vectors given by U's and V's and form a matrix M with those vectors as columns, then again, that matrix is a symplectic matrix. And from the definition of symplectic matrices, we can see that symplectic matrices are invertible matrices. So its columns form a basis of the Euclidean space R2n, and such bases are called the symplectic basis of the Euclidean space R2n. Well, symplectic matrices are analogous to or well-known orthogonal matrices from classical linear algebra in the sense that in the definition of symplectic matrices, if we replace this J with the identity matrix, then we get M transpose M equal to identity, which is the definition of orthogonal matrices. And also we know that the columns of orthogonal matrices form an orthonormal basis of the Euclidean space. So in that sense, the symplectic basis is analogous to the orthonormal basis that we know from the classical linear algebra. Just as the set of orthogonal matrices form a group under multiplication known as the orthogonal group, the set of 2n cross 2n symplectic matrices also form a group under multiplication. This is known as a symplectic group, and we denote this group by sp2n. Just like the orthogonal group, the symplectic group has some properties similar to it, such as if M is a symplectic matrix, then its transpose is also a symplectic matrix, and determinant of all symplectic matrices are equal to 1. But this symplectic group is a bit different from the orthogonal group in the sense that one of the main differences is that the symplectic group is a non-compact group, unlike the orthogonal group, which is a compact group. Moving on, we shall denote by P2 and R the set of 2n cross 2n real positive definite matrices. A fundamental result on symplectic matrices is known as Williamson's theorem, which states that given any positive definite matrix A, there exists a symplectic matrix M such that M transpose AM is the diagonal matrix given by DD, where D is an n cross n diagonal matrix with positive diagonal entries arranged in increasing order given by D1, A, D2, A, and so on. These numbers are unique for a given A in the sense that these numbers do not change if A is diagonalized using a different symplectic matrix. In other words, these numbers are called symplectically invariant for a given A. And these numbers are called the symplectic eigenvalues of A. Again, from the classical linear algebra, we have spectral theorem which in this case says that given the positive definite matrix A, we can diagonalize this matrix with an orthogonal matrix, and the diagonal entries of the diagonal matrix so obtained will be the eigenvalues of that matrix A. So in that sense, Williamson's theorem is analogous to our spectral theorem. But in a minute, we will see that even though these two are analogous notions, they are fundamentally different from each other. As a consequence of Williamson's theorem, we get, given a positive definite matrix A, we get a symplectic basis given by vectors u's and v's that satisfy for every j from 1 to n the following equations: A times uj is equal to dja times jvj, and this equation, A times vj is equal to minus dja times juj. So this pair of vectors uj, vj satisfying this condition, if we have any such pair, we say that that is a symplectic eigenvector pair of A corresponding to the symplectic eigenvalue dj of A. And a symplectic basis consisting of symplectic eigenvector pairs, when arranged like u's and v's, we say that that is a symplectic eigenbasis of A. Again, comparing it with eigenvalues, the symplectic eigenvector pairs are analogous to eigenvectors, and symplectic eigenbasis is analogous to the eigenbasis for eigenvalues. Again, both the notions are fundamentally different. For example, given a symplectic eigenvalue, we deal with a pair of symplectic eigenvectors. Whereas in case of eigenvalues, we at a time we only deal with a single vector. So, and this is also illustrated with this example. Consider a simple example where A is the diagonal matrix given by 1, 3, 4, 3. Its eigenvalues are given by the diagonal entries, which are 1, 3, 3, 4. And it's a 4 cross 4 positive definite matrix. So it has two symplectic eigenvalues, which turn out to be 2, 3. So from here, we can see that these numbers are different. And moreover, there are 4 symplectic eigenvalues, 4 eigenvalues, but only 2 symplectic eigenvalues. So given 2n cross 2n positive definite matrix, in fact, we have 2n eigenvalues, but only n symplectic eigenvalues. So even though they are similar, they are different inherently. Symplectic eigenvalues have applications in various fields of mathematics and physics. Perhaps the most important and known application is in quantum information theory, where one studies quantum states. Given an n-mode quantum state, associated with that state is a 2n cross 2n positive definite matrix known as the covariance matrix of that state. In the field of quantum information theory, an object of particular interest is the set of Gaussian states. It's because Gaussian states have nice mathematical formulations for their, that gives important properties associated with the Gaussian states. And in particular, symplectic eigenvalues are really helpful in describing various important properties associated with Gaussian states. To give you a few examples, we have the Heisenberg uncertainty principle, which can be stated in terms of symplectic eigenvalues as follows. Given a positive definite matrix A of size, of course, 2n, it's the covariance matrix of a Gaussian state if and only if each of its symplectic eigenvalue is greater than or equal to half. And there are also various entropy functions associated with the Gaussian states, such as von Neumann entropy, Rene alpha entropy, and so on, which turn out to be smooth maps of symplectic eigenvalues of the associated covariance matrices. And these entropy functions give various useful properties associated with Gaussian states, such as their degree of entanglement and degree of mixedness. So, and these functions are smooth maps of the symplectic eigenvalues. And here is a specific example, the von Neumann entropy. If A is the covariance matrix of a given Gaussian state, its von Neumann entropy is given by this expression. And the fact that x log x is a smooth map on positive real numbers implies that this expression is a smooth function of the symplectic eigenvalues, and hence the von Neumann entropy is a smooth map, can be written as a smooth map of symplectic eigenvalues of the covariance matrix of the Gaussian state.
Is this a typo? You have DJT, it should be DJA, I guess.
Yeah, it's a typo. Thanks for pointing that out, sir. Yeah, it's
okay, go ahead.
Yeah. So, given their applications and importance in various fields, it would be really helpful. It will be useful and important to study various properties of symplectic eigenvalues. We already have a very rich theory and history of eigenvalues. So a natural thing to do would be to study analogous properties of symplectic eigenvalues as we have for eigenvalues. And in the past few years, several work has been done in that direction. Several quantitative properties of symplectic eigenvalues have been studied that include perturbation theorems, some inequalities among symplectic eigenvalues of more than two matrices that are given by majorization inequalities, variational principles, and interlacing theorems. But what hasn't been studied that we found was the qualitative properties of symplectic eigenvalues. Recall the Williamson's theorem. We know that given a positive definite matrix A, there are n numbers and unique numbers that are the symplectic eigenvalues. So in other words, we get n maps given by DJ on the set of 2n cross 2n positive definite matrices. And let's call these maps symplectic eigenvalue maps, because evaluated at A, these n numbers give the symplectic eigenvalues of the positive definite matrix A. So that is going to be the focus, main focus of this talk. In this, so we'll be mostly talking about the qualitative properties such as the differentiability properties, subdifferentiability, analyticity properties of these symplectic eigenvalue maps. So here is an outline or overview of the talk. We will be talking about the differentiability properties of the symplectic eigenvalue map as functions of positive definite matrices. Then we will talk about some weaker differentiability properties given by subdifferentials. In particular, we'll be talking about Fenchel, Clark, and Michael-Pinard subdifferentials. We then study the behavior of symplectic eigenvalues for matrices lying on a curve. And in particular, we study the behavior of symplectic eigenvalues for analytic curves. And as an application of our analysis, we also give a fundamental class of inequalities between symplectic eigenvalues of two matrices AB and their sum. And we will also see that these inequalities that we obtain generalize some previously known inequalities for symplectic eigenvalues. So moving on, let's start with the basic property, the continuity. There are several perturbation theorems on symplectic eigenvalues. One of them states that given AB, the modulus of the difference of the jth symplectic eigenvalue of A and B is less than or equal to this quantity, where kappa is the condition number of A. And from this perturbation theorem, one can easily see that the symplectic eigenvalue maps are continuous functions. Talking about their differentiability, let's quickly recall the definition of derivative in general Banach spaces. Let XY be Banach space, real Banach spaces. We'll only be talking about real Banach spaces here. And let U be an open subset of X. A function psi from U to Y is said to be differentiable at a point U, at a point A in U, if there exists a bounded linear map T from X to Y such that this limit exists. And whenever such bounded linear map exists, it is unique and it is called the derivative of the function psi at A, and we denote it by, and usually denoted by d psi at A. And this derivative is also known as the Fréchet derivative of the function psi. It turns out that the symplectic eigenvalue maps are not differentiable in general, which can be seen from the following example. Consider the matrix B -1, 1, -1, 1, and define phi t equal to identity plus tb for all t in between -1, 1. And from here, it's a very easy function, simple function, and we can see that phi is a differentiable function of t. But when we compose this phi with d1 and d2, we get 1 minus the modulus function. Here, 1 plus the modulus function. And we know that the modulus function is not differentiable at 0. So here we are, there is one differentiable function. Its composition with d1 and d2 are not differentiable. So these d1 and d2 themselves are not differentiable, because if they were, their composition would have been a differentiable function. So yeah, but however, it turns out that the symplectic eigenvalue maps are differentiable under a special condition. Before we go into that, here is a quick definition. Given a positive number d, which is a symplectic eigenvalue of A, we define its multiplicity to be the cardinality of this set. In other words, the multiplicity of D is the number of symplectic eigenvalues of A that are equal to D. And we say that the symplectic eigenvalue D is simple if its multiplicity is 1, which means that there is only one symplectic eigenvalue of A which is equal to D. Rest all of them are distinct. The rest all of them are different from D. And this set of 2n cross 2n positive definite matrices is an open subset of the set of 2n cross 2n real symmetric matrices, which is a real Banach space. So when we talk about derivative of function on P2n R, so the underlying Banach space is going to be the set of 2n cross 2n symmetric matrices, which we denote by as 2n R. We prove that if the jth symplectic eigenvalue of A is simple, then the symplectic eigenvalue map dj is differentiable at that point A. In fact, we prove something more. Suppose U0, V0 is a corresponding symplectic eigenvector pair corresponding to the symplectic eigenvalue dja, then we can find a neighborhood around A such that the map dj is smooth on that neighborhood. And times U0 plus inner product of V0 plus B times V0 divided by 2. Furthermore, we also prove that there exists symplectic eigenvector pair maps uj vj, meaning for every p, uj p vj p is a symplectic eigenvector pair corresponding to the symplectic eigenvalue dj of p for all p in U. And we also compute the derivative expressions for these symplectic eigenvector maps. So to sum things up, so far we know that symplectic eigenvalue maps are continuous. They are not differentiable in general, but differentiable under a special condition. So if they are not differentiable in general, we look for the next best thing. We study their weaker differentiability properties. And there are some weaker notions of derivatives, which are given by subdifferentials, mostly found in non-smooth optimization, where one deals with non-differentiable functions. So in such cases, the tools of derivatives do not help much. And in such cases, the subdifferentials turn out to be useful quantities. In particular, they are useful in obtaining the optimality conditions. So among other differential subdifferentials, we study three kinds of subdifferentials for symplectic eigenvalues. We study subdifferential. Let X be a real Banach space and F be an extended real valued map from X to R, which can also take value infinity. its differential subdifferential at a point A is defined as the following subset of the dual of the real Banach space X. So differential subdifferential of f at A is defined as those phi in the dual of X such that phi evaluated at X minus A is less than or equal to f of X minus A for all X in the space X. And by definition, one can verify that it's a closed and convex set. It's a closed convex subset of the dual space. To illustrate this subdifferential, we consider the following map that we are all familiar with, the modulus map. We know that the modulus map is differentiable at non-zero points, but it is not differentiable at 0. But we can still make sense of its differential subdifferential, which using the definition can be calculated. And it turns out that the differential subdifferential of the modulus map at X is singleton 1 if X is positive, it is 1 if X is negative, and X equal to 0, where this function is not differentiable, it turns out to be this closed interval -1, 1. So with this example, we can see that the differential subdifferential is kind of capturing the differentiability information of the map. And the point at which it is not differentiable, it is giving us something more. So in this way, we can say that, at least in this example, the differential subdifferential is kind of a generalization of the usual derivative property. In fact, the theory of differential subdifferentials works well for the class of convex. Topology is also a convex function. It's because the convex functions have some nice properties that go well with the differential subdifferentials. We list out some properties here that will be useful in our talk and interesting on their own. If f is a convex function and f of a is a point such that f of a is a real number, then the differential subdifferential of f at a turns out to be a non-empty closed convex set. We know by definition the differential subdifferential closed and convex, still that is more interesting here. Every convex function is directionally different at this point A, which means that given any direction D, this limit exists, limit t tending to 0, t of this quotient exists as a real number. And this exists for all D. And we say that this quantity is the directional derivative of f at A in the direction D. And one more interesting property is the subdifferential of a convex map. Then using this formula known as the max formula, the directional derivative of that function can be derivative of f at A in the direction D is maximum of phi evaluated at D, where phi runs over all the elements in the differential subdifferential of f at A. So now, keeping these properties of convex functions in mind, what we do is we define a convex function associated with symplectic eigenvalues as follows. Given any positive integer between 1 and n, we define sigma m on the space of 2n cross 2n real symmetric matrices as follows. If P is a positive definite matrix, then sigma MP is defined as -2 times the sum of first m symplectic eigenvalues of P. And if it is not positive definite, then just simply define it to be infinity. Now, there's an extremal characterization of sum of m symplectic eigenvalues, which is given by this expression. It's a known characterization. If you see the right-hand side, it's minimum of trace of S transpose AS, where S varies, where S is a family of matrices satisfying certain conditions. So we can see that the right-hand side is a point-wise minimum of maps, using which one can conclude that twice the sum of first m symplectic eigenvalues is a concave function of A. And that is why we take negative sign here, which gives us that sigma m is a convex function. Now that we have a convex function associated with symplectic eigenvalues, we can certainly talk about its Fenchel subdifferential. Then we also know that it's directionally differentiable. So we can talk about its directional derivative, and we can also attempt to compute its directional derivative using the max formula that we saw earlier. And this function plays a key role in our study. So here's what we are going to do. We first find the Fenchel subdifferential of sigma m, and then using the max formula, we find the directional derivative of sigma m. And then we will show that we could also conclude that the symplectic eigenvalue maps are directionally differentiable. And we also compute the expression for its directional derivative. So beginning with the Fenchel subdifferential expression, I'll just first define some notations. Given any positive definite matrix A and M be any index between 1 and M, we introduce three non-negative integers, Im, Jm, Rm. Imagine the symplectic eigenvalues of A arranged in increasing order, and say Dm is somewhere here. Then there are Im many symplectic eigenvalues of A to the left of Dm, including Dm, that are equal to this symplectic eigenvalue. Symplectic eigenvalues of A to the right of Dm, not including Dm, that are equal to this symplectic eigenvalue. So if you are to go to the left of the left extreme, the adjacent symplectic eigenvalue will be strictly less than this left extreme symplectic eigenvalue. If you go right to the right extreme, the next symplectic eigenvalue is going to be strictly greater than this right extreme. And the sum of Im with Jm is by definition the multiplicity of that symplectic eigenvalue by Rm. To put these numbers in perspective, consider this diagram. Suppose the indices are laid down on the horizontal line from 1 to n, and the vertical lines represent the symplectic eigenvalues of arranged in increasing order. The red vertical lines correspond to the symplectic eigenvalues of A that are equal to the mth symplectic eigenvalue. So here Im consists of these many. So Im is the number of indices that are to the left of M, including M, and Jm is the number of indices to the right of M, not including M, that are equal to the mth symplectic eigenvalue, and Rm is the sum of Jm, which by definition is the multiplicity of the symplectic eigenvalue. Now, with these numbers in mind, we define delta MA, which is the set of 2n cross 2m real matrices given in the following block form. Here O means the entries are 0, and here I is the identity matrix of size M, and UV are size Rm cross Im, and so such that U plus iota V, this complex matrix, has all its columns orthonormal. So with these notations, calculate the turns out to be this. For a fixed A, suppose M is the symplectic matrix that diagonalizes A in the Williamson's theorem, then the Fenchel subdifferential of the convex map sigma M at A turns out to be the of the matrices minus M H transpose M transpose, where H varies over the set of matrices delta M we just defined. With this expression of Fenchel subdifferential that we have, and we know that Fenchel subdifferential can be used to compute the directional derivative of sigma M, we can go ahead and just do that. And using the max formula and this expression, we compute the directional derivative of the map sigma M. And it turns out to be the following expression. The directional derivative of sigma M at A in the direction B is equal to trace of B bar plus the sum of the first Im largest eigenvalues of the matrix B double tilde, where B double tilde is Hermitian matrix of size Rm, And this matrix B bar is a real symmetric matrix of size M minus Im. And the maps B bar and B double tilde are linear in B. So this is the expression for the directional derivative of sigma M. And now that we have established the directional differentiability of sigma M, we can talk about symplectic eigenvalue maps, which was our main focus. So we can write the mth symplectic eigenvalue as a difference of these two functions. So dm of A is a difference of these two sigma functions, which we know that they are directionally differentiable. By definition, the difference of two directionally differentiable maps are also directionally differentiable, and one can compute the directional derivative of this dm using this straightforward expression. So the directional derivative of dm is nothing but the difference of the directional derivatives of these two functions. And because we already know the expressions for these directional derivatives, and a direct calculation gives us the directional derivative expression for the mth symplectic out to be this expression. So the directional derivative of the mth symplectic eigenvalue at A in the direction B is negative half times the imth eigenvalue of the Hermitian matrix B double tilde.
Did you show
So
us
this was.
Did you show what is this double tilde on one of your earlier slides?
Yes, sir. So double tilde. Yeah. So this double tilde is a Hermitian matrix of size Rm that is associated with B. I haven't shown the explicit definition how that comes because it's a big one. So I'm leaving that for now. But yeah, there is this specific expression for B double tilde. Okay. So we saw the differential subdifferentials, eigenvalues, and from there we established the directional differentiability of symplectic eigenvalues. Now we move on to Clark and Michael-Pinot subdifferential. Before moving on, differential subdifferential theory goes well with the class of convex functions. So the Clark and Michael-Pinot subdifferential works well with the class of locally Lipschitz functions. So before we begin with the actual things, I'll just quickly recall the meaning of the definition of locally Lipschitz maps. So let X be a real Banach space and U be an open subset of X. Suppose F is a function from U to R. We say that it's locally Lipschitz at a point X if there exists a positive number K and a neighborhood V of X such that the modulus of f of y minus f of z is less than or equal to K times in that neighborhood of X. So this is the definition of locally Lipschitz map. And we now define the Clark subdifferential. Let F be a locally Lipschitz map on U, and let X be an element of U. The Clark's subdifferential, just like the differential subdifferential, is a subset of the dual space of X, which is the set of all phi in X in the dual of X, which evaluated at D is less than or equal to this quantity for all D. Now, this quantity is a generalization of the directional derivative, and this is known as the Clark directional derivative. So with the help of Clark directional derivative, the Clark subdifferential is defined. And the Clark directional derivative is given by this quantity, which is lim sup of this quotient where y tends to x and t tends to 0, t positive. And the fact that f is locally Lipschitz for y near x and t small, this quotient is bounded above. And that is why the lim sup exists, and we have this Clark subdifferential. Now, similar to Clark subdifferential, there is Michael-Pinot subdifferential. The definition is similar to Clark subdifferential. Here, instead of Clark directional derivative, we have a Michael-Pinot directional derivative, which is given by this quantity. And again, here we take lim sup over t positive, t tending to 0, and then supremum over y. And the fact that f is locally ellipse implies that this quantity exists for all d in real numbers. So with these definitions in mind, we now move on to the symplectic eigenvalues. Recall the perturbation theorem we just saw earlier. And from this perturbation theorem, it is easy to see that the symplectic eigenvalue maps are not only continuous, but they are locally elliptic maps. So it makes sense to talk about their Clark subdifferential and Michael-Pinot subdifferential. We find the expression for the Clark and Michael-Pinot subdifferentials of the symplectic eigenvalue maps. And we show that both the subdifferentials for these maps coincide, and find the expression, which is given by this. The Clark and Michael-Pinot subdifferential of dm at A is given by the closed convex hull of half of xx transpose plus yy transpose, where xy is a symplectic eigenvector pair corresponding to the symplectic eigenvalue dm A. And because we are here, xy is the symplectic eigenvector pair corresponding to the symplectic eigenvalue dm, this expression, and in particular this set SMA, is independent of the choice of M corresponding to the equal symplectic. The diagram where those red vertical lines we had, so it doesn't matter which index corresponding to those red vertical lines you choose, this SM is going to be the same. So this expression, so both the subdifferentials are not only equal for symplectic eigenvalues, and they are independent of the choice of M. So to sum things up till now, we saw that symplectic eigenvalue maps are continuous, but they are not differentiable in general. They were differentiable under a special condition. And then we talked about some weaker differentiability properties, where we talked about Frenchel subdifferential, Clark subdifferential, and Michael-Pinot subdifferential. We established the directional the symplectic eigenvalues, and then we talked about the Clark and Michael-Pinot subdifferentials. Now we do something else. Now, instead of talking about the symplectic eigenvalue maps as functions of all the positives, we study the properties. In fact, we study their differentiability properties as functions of positive definite matrices that lie on a curve rather than the whole set. And there we got some interesting properties. Suppose A is a curve in the space of 2n cross 2n positive definite matrices defined on an open interval script J. We showed that if the curve is differentiable at a point, then we can choose the eigenvalue maps. More precisely, if the curve is differentiable at t0, then there exist n real valued maps given by d1 tilde up to dn tilde, which are differentiable at t0. And when these maps are evaluated at t, these n numbers are the symplectic eigenvalues of at for all. And we use the notation d1 tilde up to dn tilde to indicate the fact that these numbers may not be in the increasing order. So if we ignore the ordering, we do get symplectic eigenvalue maps in this sense. And furthermore, if the curve is continuously differentiable on the interval, then these n maps can be chosen in such a way that they are also continuously differentiable on the entire interval. And we get more interesting properties when we talk about real analytic curves. So we'll talk that now. A is said to be real analytic on the interval if at every t, AT can be written as a power series, convergent power series in T. Then we say that it's a real analytic. And in short, what we find is if we have real analytic curve, then we can choose symplectic eigenvalues and corresponding symplectic eigenvector pairs to be real analytic on the entire interval. More precisely, there exist n real valued maps given by d1 tilde to dn tilde and 2n vector valued maps which are real analytic on the entire interval. Again, evaluated at t, these n numbers are the symplectic eigenvalues of at, and the pair of vectors given by uj vj evaluated at t is a symplectic eigenvector pair corresponding to the symplectic eigenvalue dj tilde a. And the set of these two evaluated at t forms a symplectic basis. In fact, it's a symplectic eigenbasis of at corresponding to these symplectic eigenvalues in this order, d1 tilde up to dn tilde. And we go one step further and talk about the properties of the symplectic eigenvalue maps, the order symplectic eigenvalue. We find something interesting. If we take any closed and bounded interval AB, which is a subinterval of the open interval say, then the map djt, which is the jth symplectic eigenvalue of at, this map turns out to be piecewise real analytic on AB. By piecewise real analytic, it means that the map dj, so it means that the closed interval AB can be partitioned into a finitely many subintervals. And in the interior of all those subintervals, the symplectic eigenvalue map Tj is analytic, and the limit of the map at the endpoints of each of those subintervals exists. So that is the meaning of piecewise real analyticity. And moreover, we also find corresponding to these ordered symplectic eigenvalue maps, a symplectic eigenbasis, which is also piecewise real analytic on AB. So as a result of our analysis, in particular, these last two results, we prove as an application a set of inequalities between symplectic eigenvalues of two positive definite matrices. And this is what we get. As an application of our analysis, we prove that given any two positive definite matrices A, B, and any k indices I1 up to ik, the sum of the of k symplectic eigenvalues of A plus B and A corresponding to these k indices is greater than or equal to the sum of smallest symplectic eigenvalues of B. This set of inequalities, it's an analog of a well-known for eigenvalues of Hermitian matrices, which is known as Litsky's inequalities for eigenvalues, which is like a 70-year-old set of inequalities result for eigenvalues, and is one of very important inequalities for eigenvalues. And here we get a symplectic analog of that particular set of inequalities. And we call this the result Litsky type theorem. And we can consider some particular instances of choosing these indices, these k indices, and different choices give different inequalities. And there are the following, it generalizes some previously known inequalities. For example, if these k indices, we choose them to be 1, 2, 3 up to k, then we get this set of inequalities for all k, which is a set of inequalities proven in 2006 by Hiroshima. And again, instead of taking k indices, if you take any arbitrary index, say j, then we get this inequality. And this is a set of inequalities for Simja and Professor Tanvijan. So yeah, I mean, I find the proof of Litsky type theorem pretty fascinating because it's, of course, an application of our earlier work. Also, it uses ideas from some different parts of mathematics. So, and the reason I kept it towards the end of my slides was because I wanted to quickly go over the outline of the proof of this result. So I'll just do that. And before starting with the outline of the proof, I'll just quickly recall some notations and results. Given an n cross n matrix A with non-negative entries, we say that it's a stochastic matrix if sum and all of its column sums are equal to 1. And we say that an n cross n matrix B is a doubly superstochastic matrix if there exists a doubly stochastic matrix A such that B is greater than or equal to A entry-wise, meaning Bij is greater or equal to Aij for all ij from 1 to n. Moving on. Associated with every symplectic matrix is a doubly superstochastic matrix as follows. To an symplectic matrix, consider its block form given by blocks A, B, C, G, where each block is of order n cross n, and form a matrix S, which is an n cross n matrix whose ijth entry is given half the sum of the squares of the corresponding entries of each of these blocks. So this matrix turns out to be doubly superstochastic matrix, and it's also a known result given back in 2015 by Professor Eigenvalue and Professor Tanvi. So now, given two vectors x, y, we say that vector x is supermajorized by vector y if the first k smallest components of x is greater than or equal to the sum of the first k smallest components of y for all k between 1 and n. And if any two vectors satisfy this set of inequalities, we say that in x is supermajorized by y. And equivalently, these conditions can be written like this. Given any arbitrary k indices I1 up to ik, the sum of the k components of x corresponding to these indices is greater than or equal to the sum of the first k smallest components of y. So this set of conditions is equivalent to saying x is supermajorized by y. And if we compare these two conditions, in the first condition, we have, in the left-hand side, we have ordering on the components of x. But in the second one, instead, we have this condition for arbitrarily chosen indices. And there is a connection between doubly superstochastic matrices and supermajorization. B is doubly superstochastic if and only if is supermajorized by x for all vectors with non-negative components. So with these things in mind, let's recall the expression for the Litsky type inequalities that we have. Again, given any k arbitrary indices, we have this set of inequalities. And from the equivalent condition on supermajorization we just saw, this set of conditions is same thing as showing that the vector dA plus B minus dA is supermajorized by vector dB, where vector dA consists of the symplectic eigenvalues of A, and so dB, and so dA plus B. And moreover, this vector that we see in the left-hand side, dA plus B minus dA, this is a vector with all its components. This is known as the monotonicity principle of symplectic eigenvalues. It's a known result. So therefore, this condition that, or into proving that d of A plus B minus d of A is S times dB, where S is some doubly superstochastic matrix. So here we are using the relationship between doubly superstochastic matrices with supermajorization. So I'll now present the proof theorem result where we are going to prove exactly this relation, and we will be done. So starting, consider the simple map D going to A plus TB, which is a real analytic map in T, because A, B are fixed. So it's like obviously a real analytic. And we know that dJt, which is the jth symplectic eigenvalue of A plus T, B, is piecewise real analytic on 0, 1. Remember, this map is real analytic on any open interval you take. So So in particular, we can conclude from the result from our analysis that this map is piecewise real analytic on the closed interval 0, 1. And as a result of our analysis, we also get 2n vector valued maps, which are piecewise real analytic and evaluated at T. This set forms a symplectic eigenbasis corresponding to A plus DB. We let MT to be the symplectic matrix like this. We know that symplectic eigenbasis gives a symplectic matrix in this way. And we know that this map DJ is piecewise real analytic on 0, 1, which implies in particular that this map DJ is differentiable at all except finitely many points. So at those points, wherever it is differentiable, we compute its derivative. And using the fact that Uj, Vj evaluated at T forms a symplectic eigenvector pair corresponding to DJ, a direct calculation shows that we can calculate its derivative, and it turns out to be this expression. Now that we have this expression, we replace B with another matrix. Now, from the Williamson's theorem, we know that we can diagonalize B with respect to some symplectic matrix M. Suppose M is that symplectic matrix, and using the property of symplectic matrix, B can actually be written as J transpose M times DD M transpose J, where DD consists of the symplectic eigenvalues of B. Now, if we substitute this in the expression for D prime J T, we do that, and we get this expression. The vector D prime T is equal to the product of matrix ST with the vector DB, where vector DB is the vector consisting of the symplectic eigenvalues of B, and D prime T is the vector whose jth component is given by J prime DJ prime T, and ST here is the doubly superstochastic matrix symplectic matrix. Remember, the symplectic group is a group under multiplication, so it's a product of 3 symplectic matrices. So it's a symplectic matrix, and ST is the associated doubly superstochastic matrix, which we saw earlier. What we do is now we integrate this equation, and integrating the left-hand side and use the fundamental theorem of calculus and the fact that symplectic eigenvalues are continuous, one gets this expression. Turns out to be D of A plus B minus D of A, and right-hand side turns out to be S times DB, where S is the integration over 0, 1 of ST. Now, one can verify easily that the set of doubly superstochastic matrices is a closed and convex set. And because S is an integration over 0, 1 of a family of superstochastic matrices, so S is actually a limit of a convex combination of doubly superstochastic matrices, and hence stochastic. And this is exactly what we wanted to prove, and hence the proof of the Liskitite theorem is over. So I end my talk here, but before that, I'll just talk about 2 possible problems one could work on related to symplectic eigenvalues. Now that we have already established the first order directional differentiability, one could also look into the behavior of symplectic eigenvalues and study the second order directional differentiability. An analogous work has been done for eigenvalues of symmetric matrices, and perhaps one could borrow ideas from there and the theory of symplectic eigenvalues to get something nice in this direction. And one could also study the equality condition of symplectic eigenvalue inequalities, such as the Liskitite theorem itself, and talk about the conditions under which given 2 positive determinant matrices, when can we expect to have equality in those various symplectic eigenvalue inequalities. Again, similar work has been done for eigenvalues of Hermitian matrices, and some interesting results have been found. So perhaps we could also get interesting results in this case. So this is it. And here are some references that proved to be crucial in our and on which this talk was based on. So I'll just quickly go through them. And that's it. And thank you. And that's it from my side. Thanks.
Hemant, sorry. Thanks. Any questions or comments?
Thank you. That was a good talk.
Thank you, sir.
Hello?
Yes, sir.
Yeah, Prof.
Hello?
Yes, sir, I can hear you. Please go ahead.
Suppose you have a Gaussian state rho, and then consider
Yes,
the rho goes to rho to the power t divided by trace rho to the power t.
Okay.
Now, correspondingly, the covariance matrix of rho will go to the corresponding covariance matrix of rho power t divided by trace rho power t. So this gives you a map from the symplectic covariance matrix to this symplectic covariance matrix, but this is a nonlinear map. This is an example of a nonlinear information Gaussian channel. Now, can theory be applied to study the smoothness of this map and how the symplectic eigenvalues change with t?
Yeah, I mean, I don't see why not, because we know much more now about the behavior, how symplectic eigenvalues change. Perhaps I could look into it, but I have a feeling that this can be done. So I don't see why not.
It will be quite
I'll have to
interesting
think about
to
it.
see. Yeah, it will be.
Yeah.
So what is the relationship between the Gaussian state, this rho power t by trace rho power t? What will be the covariance matrix?
No, rho goes to rho power t divided by trace rho power t.
That's the covariance matrices we are talking about.
This is an example of a nonlinear Gaussian channel.
Okay.
So this gives you a map. Now I want to know whether the eigenvalues of the image Gaussian state as a function of t, as a function of rho, that is, rho is the input state, and you have rho power t by trace rho power t is the output state.
Output state.
So there are innumerable examples of what are called nonlinear channels. Now, and then correspondingly, the covariance matrices will completely determine these Gaussian matrices. Gaussian states. And I would like to know whether there can be an expansion for the eigenvalues of the output in terms of the eigenvalues of the input.
Okay. Yeah.
And this is a general problem, but I don't know whether these techniques can be applied there.
In principle, there should be, but exactly the how the covariance matrix according to the Gaussian state, I think that will depend. That will play a role. How what will be the corresponding mapping on the level of covariance matrices? That will actually play the role in computation. In principle, I think they should be, but
the question is there a simple expression for the covariance matrices of this channel? I think that is what would determine the answer.
Yes.
Yeah.
Hello, Hemant, I have a question.
Yeah. Yes.
Am I audible? Yeah.
Yeah.
So I'm curious to know the applications of these matrices in quantum information and computation, as you discussed. So are these matrices always Hermitian?
Yeah, I mean, the covariance matrices are more than Hermitian. They are
Matrix M, matrix M.
real symmetric positive. Sorry, sir?
Okay, so matrix M.
No, M is
So,
not
so,
M is a symplectic matrix that he's talking about. I think.
so
Yeah.
you have written an equation M transpose J M is equal to a diagonal matrix. Fine.
Yeah.
So you are doing diagonalization of a matrix J through M.
No. Just a minute. J is not diagonal. So
No, J is not diagonal, but in the right hand side we are getting a diagonal matrix. So it will be a special case of similarity transformation. Fine. So M transpose should be equal to M inverse. Hence M must be also a unitary matrix. Am I right?
No. I think you're mixing two different things. There is A which is being diagonalized by M.
Yes. So I am interested in the structure of M.
So M TJM is equal to J. It's not diagonal. J is not diagonal. So it's A which is being diagonalized by a symplectic matrix.
I think so. It's a special case of similarity transformation, right?
It is not exactly a similarity transformation because it's like
in
a
matrix
congruence.
Given a matrix A, we want to diagonalize it. So we want to find out the matrix M that can diagonalize A. So what will be the structure of M here?
That A, basically that M we are looking at is from the special class of symplectic matrices. So Williamson theorem tells us that there is a symplectic matrix that diagonalizes A in that special manner. So we are looking at that class of symplectic matrices.
M is not M transpose is not M inverse.
So your voice is not.
Just saying that M transpose is not M inverse. So this is not similarity. It's some kind of congruence which is different.
Okay. So through this technique, we can also diagonalize a given matrix A, right?
Yeah. So
Hemant,
so to answer your question, I mean, so the goal is not to just diagonalize. So here the goal is to diagonalize from taking a matrix from a special class of matrices, because we already have the set of orthogonal matrices and spectral theorem which does the job for us. So here we are specifically talking about symplectic matrices, and the Williamson theorem guarantees that you can diagonalize A with respect to symplectic matrix, and this diagonal matrix is of spatial form. So that's about it. But if you are interested in the structure of symplectic matrices diagonalizing A, then one would have to maybe work case by case. So, for example, if you want your matrix to be...
Will it be any arbitrary matrix, or can we form this matrix by the eigenvectors of A?
Yeah, so regarding that, there is, it's a good question now that you have raised. There indeed is a relationship between eigenvalues and symplectic eigenvalues. The symplectic eigenvalues of A turn out to be the positive and negative eigenvalues of the matrix iota J A. So maybe I'll just quickly just explain that in here. I'll just give me a minute. I'm just connecting with my.
Okay, no problem.
Yeah. So we have symplectic eigenvalues of A, which are these n numbers. I'll drop A here corresponding to A. It turns out that these symplectic eigenvalues are nothing but plus minus the... So we have n symplectic eigenvalues for A. And if you consider this Hermitian matrix, iota A power half, J times A power half, this is a Hermitian matrix. And its eigenvalues are given by these 2n numbers, d1 plus minus d2 and so on up to plus minus dn. So in this way, there is the symplectic eigenvalues are connected with eigenvalues of this associated Hermitian matrix. And regarding the eigenvectors, yes, there is also a relationship between them. For example, if corresponding to the symplectic eigenvalue, say dj, we have this eigenvector of this Hermitian matrix given by a complex vector x, say it is u minus iv, where u, v are real vectors, then the symplectic, then it turns out that a power minus half u and a power minus half v, this pair turns out to be a symplectic eigenvector pair corresponding to the symplectic eigenvalue dj. So yes, with this relation, they are connected. So, yeah.
Thank you so much. Thank you.
Sure.
So there are two, Deepak and Sushil, they've asked on chat. So now Deepak and Sushil, you can mute one by one and ask.
Hello, am I audible?
Yes, yes.
Yeah, so what I had asked actually was that you had said that for any map, the subdifferential will be weak star closed and convex.
Yeah, it will be closed and convex, yes.
So is it for any function f or is it for the continuous and convex function f?
It's by definition for any function because
no definition
again yeah. So I'm just telling you that it's closed and convex for any function, not just closed, not just continuous or convex function. So if you recall the definition, it's this. It's all phi in x star such that phi evaluated at x minus a is less than or equal to f of x minus f of a for all x in x. So this function is convex because if you take any phi1, phi2 in this, and it trivially satisfies this condition. And continuity, because
continuity guarantees non-emptiness, right?
Non-emptiness is guaranteed by the continuity doesn't guarantee non-emptiness. The convexity is what guarantees non-emptiness. In fact, there is an example. Sorry?
Continuity and convexity are required for non-emptiness, right?
Yeah, well, if a function is convex, then it's a locally Lipschitz map. So continuity comes along with convex functions. So yeah, once you're assuming convex function, it will be continuous also. And to give you an example, consider this minus of modulus of x map. This map is all, it's very nice map. It's continuous, it's convex, it's concave, but still its Frenchel subdifferential turns out to be an empty set. You can just work it out, and it turns out to be an empty set. So it's the convexity that plays a key role in that.
So Hemant, may I ask one question?
And again, yeah, please go ahead.
In your work, you used symplectic basis for R2n, right?
Yes.
Symplectic basis. So in R2n, very well-known bases like orthonormal bases are available there. So what's the difference between symplectic basis and orthonormal basis?
Yeah, I mean, the difference between ordinary orthonormal basis and symplectic basis is similar to the difference between orthogonal matrices and symplectic matrices. You see, the columns of symplectic matrices give symplectic bases and columns of orthogonal matrices give orthogonal bases. So the difference is in the definition itself. Like orthogonal basis means the vectors have unit modulus and their inner product, mutual inner product is 0. Yeah. And in case of symplectic
but they are,
in case of symplectic.
No, I mean, other than orthonormal basis, I mean, Hamilton basis is also there. So in your work, there is some structure of this basis. There is any special structure of this symplectic basis is used in your work? I mean, you use. I mean, basically, what is that? It is, linearly independent generator. Okay, right?
Basically, the symplectic inner product relationship.
Yeah.
Okay. Yeah.
Yeah. I mean, in that sense, there is this symplectic inner product on which the symplectic theory is there, and we have this inner product, usually inner product, on which we have the theory. So there is this symplectic inner product, and symplectic matrices are precisely those matrices that preserve those symplectic inner products, and orthogonal matrices are those matrices that preserve the usual inner product. So in that way, they are analogous.
So, Mr. Hemant, any relation between orthonormal basis and symplectic basis in our way? In some way they are connected.
Yeah, there is. In fact, a matrix M is both symplectic as well as orthogonal matrix if it has a specific structure. If it is of the form U, V minus V, U, where U, V are n cross n real matrices, such that this complex matrix is an unitary matrix. Because it's a complex matrix, so we'll use the term unitary matrix.
So what do we conclude from here?
So basically,
I mean, this is a relationship.
Between?
Yes, ma'am.
Yeah, basically, see, he wants to have that. You talk about orthonormal basis. There, the vectors are orthogonal. Yes, of unit vector and unit vector. So in symplectic basis, we have the pair of vectors. So that are normalized. So if I have u1, u2, un, v1, v2, vn, those will be 2n vectors. They'll form a symplectic basis if I have ui, j, vi. That is, the symplectic inner product between ui and vi is 1. And the symplectic inner product between any ui, uj or ui, vj when I not equal to j is 0. So it's something like an orthogonal, this inner product. But it's exactly not an inner product, it's a bilinear form. That's the relationship. Also, so as to say, the analogous thing for symplectic basis and orthonormal basis. But they're different.
Thank you. I just first time I want to know that this type of basis also exists. Actually, this is a very interesting.
Yeah.
Actually, I am working in frame theory.
So Hemant, just 1 second. I think people continue to be bothered by this convexity continuity business. So just 2 comments. He was looking at open intervals, so it's okay. And second, these are continuous functions in any case, so don't worry about it, just assume continuity. But if you take an open interval, then the bad examples come from taking closed intervals, if I remember correctly. So on open intervals, you are okay. Yeah, go ahead.
Any more comments or questions? Sorry, I couldn't hear. Anyone wants to ask something? So if there are no more questions, let's thank Hemant. And I would like to thank all of you to for joining us in this pandemic time and these are difficult times. So, and wish you a safe stay. So, thank you.